Welcome to our first lecture on wireless communication. I hope you all have revised the basics of probability theory because that will be used in subsequent lectures. So the first thing we would like to study in wireless communication will be the point-to-point channel. Because the fundamental model in wireless communication will be there will be some transmitter and there will be some receiver. Okay. Although if you take any general communication system like the mobile communications, there are a lot of mobiles communicating with each other with the base station, so that we will take up later. But fundamental model of communication system is there is some transmitter and there is some receiver. Okay, so we first want to come up with a appropriate mathematical model, after which we will like to analyze the system. So for that we would first like to represent the input and output. Now in modeling the system, the first question will be, what is the transmitter and what does the transmitter emit? What does it want to send? So you have done the basic course on communication system, and there you have learned two type of modulation schemes. One is the analog type, in which we have studied AM, FM, and the other one was the digital modulation schemes, in which you have studied basics of BPSK and I think QPSK and maybe MPSK. Okay, so first of all, we know all the cellular systems starting from 2G and 3G, and now we are into 4G and we are going towards 5G, and even people are now talking of 6G communication systems. So they all are now fully digital. Okay, they are using digital modulation schemes. We no longer use AM, FM, and we use digital schemes. Suppose 2G started with QPSK, and then we moved to 8PSK, then of course 16 QAM, and in 5G we even talk of 64 QAM modulation schemes to be used. So it's time for digital. So the analysis will be done with respect to digital modulation schemes. So transmitter will use any appropriate digital scheme. Now for analysis purpose, we will start with BPSK, okay, because it is easy to analyze. We'll start with BPSK. A brief recap of what is BPSK. You all know it stands for binary phase shift keying. We know in digital world, especially for binary case, we have to transmit. So here's the sequence. I will again recall the fourth semester communication system. So you basically have analog signals, and then you go for sampling, and then after sampling you go for quantization and you do pulse code modulation, and finally you get zeros and ones, right? Now you want to first represent them. So for representation purpose, you represent one by some positive signal with some amplitude, suppose root p, or for binary 1, and for binary 0 you represent it with this pulse with minus root p as amplitude. Okay, so that the overall power is p. So this is how we represent it. And in terms of waveform, how we represent it is that we have a carrier signal to root 2 by t cos of 2 pi fct. Fc is the carrier signal. So this carrier signal is transmitted for the time period t, and if it is binary 1, will transmit under root of 2p by t cos of 2 pi fct, and if it is binary 0, we give a phase shift of pi, so 2 pi fct plus pi, which all of you know is minus of root 2p by t cos of 2 pi fct. Okay, so this is what we call also as pass band, that is we are transmitting it over the antenna, this signal. But if you recall, I have told you something called baseband. In baseband, it means that before the modulation, how will you represent the signal? So that representation I have shown here. Okay, so then we call this as BPSK symbol. BPSK symbol is now plus root p for binary 1 and minus root p for binary 0. So in baseband, let me represent the transmitting symbol, which is here BPSK symbol, as x of k. This is the transmitting symbol. Okay, now you may say, what is this k? actually you had x of t, right? It is a continuous time signal, but when you sample it, so you are now having x of k. So k is now the time index but discrete. It is actually a sample number. Okay, so x of k is a particular sample which represents the symbol which is transmitted by transmitter. So for BPSK case, x of k can either be plus root p or minus root p. Later on we can also use QPSK, MPSK or QAM. Accordingly, x of k value will change. Now what you receive at the receiver, here you represent that as y of k. Okay, this is x of k. And the noise, so there is a noise at the receiver which is getting added up. So let's represent that noise by n of k. So this is the noise at receiver. Okay, and this is what you see as y of k is x of k plus n of k, and this is the additive channel model, additive noise channel model, right? The noise gets added up. So there is a specific reason for why it gets added up and why it doesn't get multiplied. Okay, and that we will do later on. Right now, the one more thing you have taken into consideration is that transmitter receiver, there is no, you can say, hindrance in between. It is sort of a transmission line actually. Okay, you can think of a transmission line. So there is no shadowing, there is no reflection of the signal. So there is nothing in between transmitter and receiver. So either it is a point to point sort of a line of sight communication. So here is a transmitter antenna and here is a transmitter receiver antenna very nearby, and there is nothing in between, and direct transmission. Or you can think of a transmission line, okay, just like a telephone line or any LAN wire. So there is no time variation of the signal. Okay, so what you receive is simply what you transmit plus the noise. Noise gets added up at the receiver. So in receiver you will have definitely amplifiers, and you will have multiplexers, demultiplexers, you will have demodulators. All those have a common thing, they have a transistor. Okay, and transistor at the electronic level becomes a source of noise. So the noise which is getting added up here is at the receiver, it is not in the medium. Okay, that is our next topic in wireless communication. What happens if there is reflection? What happens if there are different obstructions in between the transmitter and receiver? So right now this is our model. Okay, so we are now very much clear. We have input as right now BPSK symbol, we have a noise. Now we have to model this noise. How will we model this? To understand the noise model, I would like to introduce you to one important theorem in probability theory, that's called central limit theorem. Central limit theorem speaks about if you have a random variable, suppose x1, x2, and you have n random variables. Okay, what happens when you add up all the random variables? What happens to the distribution of this sum? Okay, you can represent this as I is equal to 1 to n xi. So the question is, what is the distribution? Now for that we will first recall, if you have just two random variables, suppose x1 plus x2. Okay, suppose x1 has probability density function fx1 of x1, x2 has fx2 of x2. Then if you define, suppose y is equal to x1 plus x2, what will be the PDF of y? So without proof, I will directly tell you, the PDF of sum of two independent random variables is the convolution f of x1 convolved with f of x2. Okay, so this will be the PDF of y. So how you define the convolution? Since it is, I have taken x1 and x2 here as continuous random variables, the convolutional operation is integral. So fx1 of x1 and fx2 of y minus x1 dx1. Okay, so this will be the convolutional operation from minus infinity to infinity, and this will be the PDF of the sum. Similarly, if you have three random variables, if you add up one more x3, then you will have to convolve with fx3 of x3. The condition is that x1, x2, x3, they are independent of each other, that is one thing, and they are identical. Identical means their mean, their variance, their distribution, everything is same. So if x1 is Gaussian, or if x1 is suppose uniform random variable, so is x2, so is x3. Okay, and this can be even generalized to n random variables. If you add up n random variables, the distribution of sum of these random variables will be the convolution of distributions of x1, x2 and xn, so on and so forth. Now what does it tell about as n increases? Okay, if you increase the n, and in fact if this n tends to infinity, how does the distribution look like? I will give an example for that. Here is one example. Suppose you take x1 and x2 both as uniformly distributed random variables, that their PDF probability density function is uniform PDF. What is uniform PDF? So the uniform PDF is something like this. Let's take a simple case. Suppose it is 0 and 1, and this is fx1 of x1, this is x1. So random variable can take any value between 0 and 1 with same probability density function, constant. Okay, so that is why we call it uniform. Or let's choose another one. So it is something like this, between -1 and 1. Okay, it will choose the random, it will choose any value between -1 and 1 with equal probability density function. Okay, what will be the height? You know that the PDF satisfies this property that its integral over all values is 1, that is the area under the curve will be 1. So this distance is here 2, so for area to be 1, the height should be half. Okay, now suppose x1 is one random variable having this uniform distribution, x2 is another random variable having this uniform distribution. Now when you add x1 plus x2, the distribution of x1 plus x2 will be the convolution operation between them. The convolution of two rectangles, as you can see, that it is the integral of the product of two PDFs. Both are here uniform, constant, so its integral will give a linear shape. So you just do this small exercise for verification, you will get that the PDF of sum of two uniform random variables is something like triangular, because you are integrating a constant thing. Integral of c dt is ct, right, plus constant. Now if you add up third random variable, so then you will have to convolve with rectangle with triangle. What does it mean? Suppose this is the PDF of x1, this is PDF of x2, this will be PDF of x1 plus x2. Now if this is x3, now you want to find PDF of x1 plus x2 plus x3. So x1 plus x2 has PDF, this triangular, and then x3 is again a uniform random variable, same uniform random variable. So you want to add it up. What will be the overall distribution? Now it will be the convolution of rectangle with triangle. So triangle, if you see, it has a linear term t in its equation. So if you integrate it, it will become t square by 2. So when you convolve rectangle with triangle, it will become sort of a parabola. Okay, now suppose I now add up one more random variable x4, which is again uniform random variable. What will be its distribution? So you are basically doing x1 plus x2 plus x3 plus x4. Now x1 plus x2 plus x3 has this parabolic type of distribution. Now you have to add up one more uniform random variable x4 to it, so it will be now convolution of rectangle with parabola, so it will be something cubic type of curve. So now what will happen is this tail will start going up, because a cubic term has a tail. So what happens when you add up? Same way you add up infinite random variables. You take this n, limit n tend to infinity. So there is a rigorous proof of it. I am just demonstrating it here. You will find that the overall distribution looks like this. This is called the bell curve, and its equation is 1 over under root 2 pi e to the power minus some x square by 2, and this is what we call as standard Gaussian random variable. Okay, so far so good. Now you may say, nice, central limit theorem, but what it has to do with the noise? Now coming back to the transistor model. In transistor, your incoming signal is nothing but a current. So it is actually all about the motion of electron. Suppose this is your incoming electron, whose motion represents the current, which represents the signal, input signal. Okay, suppose that x of t, that is represented by the motion of this electron. Then inside the transistor there are billions, trillions of electrons which are moving randomly. Okay, they are moving randomly. So when this electron enters into the solid state device, okay, that material, so it will encounter these different electrons. So first of all, the electron, the current from the electron is determined by the change in the velocity, right? Change in the drift velocity. So let me take a vector vi, input velocity of the incoming electron. Okay, it's a vector, right? And then there are these electrons, let their velocities be suppose v1, this is v2, this is v3, this is v4. Okay, what will happen when they collide? So the resultant velocity, okay, that will be vi plus v1 plus v2 plus vn. There are n electrons, right? Now electrons are moving randomly. If you you might have studied this, that they follow a Fermi-Dirac distribution, and they're also called fermions. So you can think of electron motion, their velocity, as a sort of random variable with a particular distribution. So what is happening here is we are adding up these n number of random variables, and remember that number of electrons in any material is so high, you can take that this n actually goes to infinity, tends to infinity. So now you have an infinite number of random variables. Now you invoke the central limit theorem. What it says that when you add up infinite number of random variables, the resultant distribution will be of, Gaussian distribution. Okay, so their distribution will be Gaussian, and this is what actually is the source of noise. Okay, I will call that Vn. Now the correspond to the velocity of incoming electron, you have the signal representation x at time instant k, plus corresponding to the disturbances because of other electrons, you have the noise at the same time, n of k. And now this n of k, we call it a Gaussian noise. Okay, it follows a Gaussian distribution, bell curve, right? And this completes the channel modeling. So you have a channel in which noise gets added to the input process. The another important property of this Gaussian noise, which you might have done in the random process course also, is that if you see this noise process as a random process, its power spectral density is constant with respect to the frequencies, something like this. Okay, suppose you are working in the bandwidth of b hertz, and this is the PSD, it will be constant. Usually we represent it by n naught by 2, the height of this power spectral density. And the same is the property of white light. If you plot the intensity of white light versus the frequencies, so each frequency component has same contribution in the white light, hence this is also called white Gaussian noise. Okay, white Gaussian noise. So the channel is called additive white Gaussian noise channel. Okay, AWGN channel, right? So we'll do this much in this class. We have completely characterized the channel model. We know the input, how to represent it. We know the noise, how to represent it. Now our next job will be to identify if we transmit suppose 1 or binary 0, what will be the effect of noise. Definitely noise will change the value. It may sometimes change 1 to 0, 0 to 1. Then our question will be, what are the chances of errors to occur? In other words, what is the probability of error? In other words, we also call what is the something called bit error rate. Okay, BER. So in next video lecture, we will do the bit error rate analysis of this AWGN channel when we take the input from BPSK. Okay, because once you understand BPSK, we can easily understand BER analysis for QPSK, QAM. They all follow then same principle. Okay, so revise this. I will again request to revise the probability theory, because you see that will be used heavily in these lectures, and go through it properly. And in next lecture we will derive the bit error rate expression and define some important functions like Q function, which will be used in the subsequent lectures. Thank you.